All right, let's talk about the conservation of energy. So energy, there's just like everything else, energy has units, and those units are there to help us know how much is there. And the energy we use is called joules, the Joules. It's much like Newton's in force, only we're talking about energy. You say you have joules. Well, how much energy are you packing? Packing 100 joules or 200 joules or whatever it may be. Now we talked about mechanical energy last time with it being our total energy. Okay, it's all our potential added to all our kinetic. And in most cases, it's just going to be a few potentials with the kinetic. And at times it may just be a few potentials, and sometimes it'll be a lot of other stuff. Okay, but we talked about it being the mass times the gravity times the height of the off the ground of that object. And we've talked about this equation, 1/2 times the mass of the object times its velocity squared. Okay, and our spring elastic. Now, let's do a quick example of how to solve for this equation. So Jane, there she is standing on her thing, 52 kilograms is on her high dive. The high dive is 5 meters tall. How much gravitational potential energy does Jane have? Well, if you remember, our equation is gravitational energy is equal to the mass of the object times the acceleration of gravity on that planet times the height. Well, Jane happens to be our object, and she is 52 kilograms, and our mass is in kilograms, which is what we always want it to be in. So 52 times by the acceleration of gravity, since we're on Earth, that's going to be 9.8 times by the height. She is at 5 meters, so that's times 5. You always want this in meters as well. If we do 52 times 9.8 times 5, that is going to equal, if we solve for that, that is equal to 2,548 joules. Okay, that is how much gravitational energy she has. Now, throughout this situation, see how she's kind of in that box on the high dive? Throughout this situation, she is going to have that much. Okay, so here's our kinetic example. As Jimmy, 75 kilograms, watches Jane jump, he gets nervous and runs 5 meters per second towards the edge of the pool to make sure she isn't hurt. How much kinetic energy does Jimmy have? Okay, let's look. Remember, kinetic energy is equal to 1/2 times the mass of the object times its velocity squared. So in this case, Jimmy happens to be our object, so it is going to be 75 is our mass. We have to times that by 1/2 times its velocity squared. Its velocity happens to be 5 meters per second. It's in meters per second. This is exactly what we need it in, times 5 squared. We solve for that, and that comes out to be 937.5 joules. There she goes. Jimmy running to save her. Our spring elastic energy. Okay, so you've got to do some work. Work equals force times distance, so we've got to apply a force to the block, move it a certain distance, and that's going to be our work. Remember, force is just mass times acceleration of the object. How much force does it take to draw back on a bow a small amount? Does it take the same amount of work as if you draw it back all the way? So you realize that just pulling it back a tiny bit doesn't take that much. There's not that much force involved, and there's not that much distance, so there's not as much work. But if you were to pull this bow the entire way back, you realize that it takes a lot of effort. It's being stretched quite a bit, so you have to use quite a bit of force, and its distance was a lot more. So the work that is in this situation is much more than the work in this situation. Okay, there's our equation, potential spring equation. 1/2 kx squared. Okay, remember k was how much the spring constant, so the stronger the spring, the bigger the number, or elastic. So a bigger rubber band is going to have a bigger k than is a smaller rubber band. X is the distance that it was compressed. Let's move myself out of the way. Is the distance that this spring is then compressed. Okay. So let's look at a practice problem with Jane. If Jane can store 435 joules of energy in the ballista spring, how far back will she be able to pull the bowling ball if the spring constant is 7? Okay, so this is an energy problem, and if we want to look at it normally, we can tell that we've got energy here, we've got a number here, and we're trying to figure out what we're solving for. So we know the equation is spring energy is equal to 1/2 kx squared. So right here we have our energy, 435 joules of it. We know our spring constant. There's two variables. We only have one variable left, so this is a solvable problem. Plug in our numbers. 435 equals 1/2 times k, which is 7. We just grab that right out of the problem and put it in, times x squared. Okay, now we just solve for x. Times by 2, times by 2. Those 2's cancel. We get 435 times by 2 is equal to 7x squared. Now divide by 7, divide by 7. Those 7's cancel. We are left, let's draw it right up here, with 435 times 2 divided by 7 equals x squared. Now we just square root. Square root. We get 435 times by 2 divided by 7. All of that square rooted equals x. And x we find out to be is 11.14 meters. In other words, Jane's ballista, or her little bowling ball, should be able to be pulled back 11.14 meters. As we see, she launches, she gets Jimmy, and he gets blown away.